Well, all right. So the big topic here is really quadratics, and that's really an important topic moving forward into college algebra as well. So this is something that's going to be covered thoroughly on the final exam as well, as I want you to be good at solving quadratics. And we've got a couple different strategies for quadratics. Remember, a quadratic looks like ax squared plus bx plus c equals 0. So they can look different than that, but they should all be able to be written like that. So you may have to do some rearranging or distributing, sort of moving things around to get them to look in this form. And this is called standard form. And it's really where we'd like to have quadratic equations. This is sort of, it's a good name, standard form. The only rule there is that a cannot equal 0. So you have to have an x squared term or else it doesn't count as a quadratic. But you don't have to have the x term or the constant term. Those may or may not be there for different kinds of quadratics. So when you have a quadratic, we want to solve it because we're talking about quadratic equations here. And you should have noticed that there are typically two solutions. Sometimes those solutions can actually be the same solution, so you may end up with only one distinct solution, but typically there are two different ones. So we're always kind of looking for that and making sure that we have or have sort of accounted for both of those solutions. And the first method that we like is factoring. So factoring is a great method. If you have a quadratic like x squared plus 8x plus 12 equals 0, this is a perfect one to do by factoring. It's a pretty easy problem to factor. We have x plus 6 and x plus 2, right? That combo multiplies to give me 12 and adds up to give me 8. So that leads very quickly. You can kind of skip this intermediate step if you want to our two solutions, x equals -2 and -6. So factoring is great in that situation and really the best method in that situation. We also have what's called the square root property. And the square root property also has its place. It's very effective for certain types of quadratics. If I have, say, 2x plus 3 squared equals 7, notice this is not written in standard form. If I wanted to write in standard form, I would have to FOIL this 2x squared plus 3 out and then move the 7 over, which I could do. It turns out that's a lot of extra work, and you end up with a quadratic that's not even all that easy to work with. This is a great candidate for the square root property as it's written. So 2x plus 3 squared equals 7. The square root property says that 2x plus 3 must equal plus or minus the square root of 7. A lot of people think of like taking the square root of both sides, which is sort of what we're doing, but not exactly, because we get two values here, right? We get plus or minus, and that's important. You cannot forget that, because if you do, you're missing half the solutions, and that's gonna ding you a little bit, right, on your problems. Now we still have a little work to do to find x. We can subtract the 3 from both sides, and it's easiest to just keep this plus minus in the problem till the very end. Plus minus the square root of 7 over 2. And that's actually two solutions, and what you've seen on WebAssign is that there's no plus minus on WebAssign, unfortunately. or fortunately, it's not actually that bad, because it makes you write them out as two separate solutions, which I sort of think is a good thing in some sense, even if it is extra work, okay? So that is the most efficient method for this type of problem. Factoring, even if you got this one in standard form, there's no way you're going to be able to factor it. And you can see that by the answers, right? This answer can't come from this kind of factored problem, right? So the square root property is nice, and it also works in certain situations when factoring does not. I'll go down here. We also have this method called completing the square. And this method is really like a precursor to the quadratic formula. So in some ways, the quadratic formula replaces completing the square, but I am likely to ask you at least one completing the square problem, because that is actually the method that leads to the quadratic formula. So the quadratic formula is sort of a refinement or an improvement on completing the square. We don't like formulas that we don't understand, or I don't like formulas that you don't understand. So I make you do a little completing the square. But we will keep that one pretty simple. Right, so I won't have any coefficient in front of the x squared. Now I'll keep this number an even number. Those are some things that make completing the square easier. When you're completing the square, you're trying actually to turn it into this, because this is a form I know how to solve. And the way to do that is to move the 5 over, and then you add something special to both sides to keep it balanced, because it's an equation. And the special thing is always half of this number squared. Right? So half of 8 squared is 4. 4 squared is 16. So I'm going to add 16 to both sides. What that 16 does is it turns this problem into one that can factor. And it turns out it's going to be x plus 4 times x plus 4. So that's the completing the square part, is just making this a perfect square when it factors. And that's great for us because now this problem is really exactly like this problem. X plus 4 is plus or minus the square root of 11. So x equals minus 4 plus or minus the square root of 11. So you got to remember that this one is like a two-part problem, right? One part is to get it into that form, and then the second part is to solve it. And if you watch the lecture, you probably would have seen me do this. If you make this just a general ax squared plus bx plus c, and you do this whole process, you end up with the quadratic formula. The quadratic formula is a shortcut to completing the square, where these a, b's, and c's are the same as this a, b, and c. And you should know this or write this down on your note sheet. The quadratic formula works for any quadratic in standard form. So it can work for any quadratic. And that's really nice, right? All these other methods really only work for kind of special cases, right? Things that factor, or things that fit the square root property, or things that we can complete the square. The quadratic formula works for everything. So if you're going to only know one of them, the quadratic formula is good. However, it's kind of a pain. You have to do a lot of little algebra steps to get to your final answer. So these methods are really better if they're used on the right problem, right? But if you get stuck or you can't do it, you can use the quadratic formula. let's look at 3x squared minus 2x plus 5 equals 0. We make that plus 6. So we identify the A, the B, and the C. And this goes right to our solutions. The opposite of B, so B is -2, the opposite is +2. Plus or minus the square root of B squared. That's always positive because I'm squaring it. This is a spot where a lot of students make an error. You got to be very careful with the signs here to make sure that you keep track of whether that's positive or negative. And that's all over 2a. So that part is actually, or should be, pretty easy, right? You're just taking A, B, and C and plugging them into the formula. It's the next parts that are a little more challenging. You've got to figure out what the square root is first. 4 times 3 is 12. 12 times 6 is 72. 4 minus 72 is -68. So I've got to simplify that a little bit. The negative comes out as an I, right? That's a complex number. We always want to pull negatives and square roots out as the imaginary value, or I. And then 68, well, that's 2 times 34. So I can pull another 2 out. That's 4 times 17. So the square root of 4 is 2. So -68 has a 4 and a negative. That comes out as the 2 and the I, and then the 17 is left over. That's all divided by 6. And I have to be careful here. The only way I can cancel is if it's common to both of these top terms here. And there is a 2 both of those, so that can cancel with the 6. And that's going to leave me with 1 plus or minus I squared roots of 17 over 3. I hope you can see from that example why the quadratic formula is sort of not our preferred method, right? It was like a relatively straightforward quadratic. But it took us a long time to finally get to our answer, right? A lot of steps. Okay. Questions about that? I guess that took me a little longer than 10 minutes. Not too bad, 15 minutes. Are there any questions about any of those processes or? Yeah, so good question. So the question is like the I here. The I, I'm sort of out of paper, so let me move here. When I take the square root of something like -8, I think of it as kind of the -1. I think of pulling the perfect squares out in front. And so the square root of -1 is I, and the square root of 4 is 2, and the square root of 2 is just the square root of 2. So these 3 things are just multiplied together, and you can multiply those things in any order you want. I can put the I in the front or the back or the middle. I can switch things around. They are all the same. The problem is that sometimes if I try this method, I see it fairly often that students will write this. And notice here the I has kind of crept inside the square root. So now it looks like the square root of 2I, which is not the same thing. Okay. So while it's not incorrect to write this, I'd say it's a little dangerous to write that. And this is really the preferred form. It's the same with an x, right? We kind of like to put it like 2x rather than x times 2, even though they're the same things. So we prefer that, and I think it's safer, but technically they are all the same. So it's a good question. It's like this new thing, right? Like how do we work with it? How does it fit in with what we know? And of course, the key is really two things. The square root of -1 is I. That's what we're using here, and that's probably what we use the most moving forward. But we also, if the square root of it is I, then I squared has to be -1. So if you see a square root of a -1, you want to turn that into I. If you see an I squared, you want to turn that into -1. These are sort of simpler things here on the right side. And I think for students, it feels weird. I mean, it's called the imaginary unit, which I sort of hate the name because it sounds made up, right? But it's just as made up as like the number 2, right? The number 2 we have no issues with, but it's an idea, right? 2 is an idea. It's a symbol that represents something. And I is a symbol that represents something. So it just functions differently than real numbers, right? And that's why it's called an imaginary number or imaginary unit. It's kind of like a bad pun, right? Like real numbers sound fine. Well, if you're not a real number, then you're an imaginary number, right? But it's not made up. It just, like I said, just represents an idea. That's what numbers and symbols do in math. That's what vocabulary does in any subject, right? You know, biology has all kinds of terminology that represents something, and math is no different. Other questions? Oh, I didn't scare anybody off by taking that long answer to that question. But any other questions we should look at, or anything from the homework that you'd like to go over?
The fractions, we're trying to get like the common denominators with the fractions with variables kind of confuses me sometimes.
Yeah. Let me think if I. Let's make this. I don't know. Let's try this. Does this look kind of like the problem?
Yeah, this is it. Thank you.
Okay. Yeah. So well, actually here I can make it, since we know what we're doing here, we can actually make that just 3 and see what this leads to. So you're exactly right in that you kind of need to deal with the common denominators here. A general rule is that if you have an equation that has fractions, like this is an equation, equal 3, it has fractions. Our goal is to get rid of those fractions. So rather than sort of like adding them together like we normally might with a common denominator, I mean, it looks a little bit like addition here. I don't need to do that if it's an equation, because I can get rid of those denominators. So what I'm going to do is, like you said, if it has variables in it like this, I'm going to start by factoring it. Because factoring is going to sort of show kind of like what's underneath. That's what I think of as like factoring sort of exposes the core of the thing. Right? Like 3x minus 6, I don't know, but when I break it down, then I can see it's like elements, right? Elemental pieces. So what I see here is that I have a 3, an x minus 2. Over here I have an x minus 2 and an x plus 2, and over here I don't have anything. So if I want to eliminate these denominators, I'm going to have to multiply each of these three pieces. To keep the equation the same, I got to do the same thing to all three of them, whether I want to or not, right? I got to keep it balanced. I'm going to multiply each of them by a 3, an x minus 2, and an x plus 2. That is technically the LCD, but it's also just like the smallest thing that includes kind of all of the terms, right? I'm imagining if I multiplied everything by those three things, that's going to be enough to cancel. My whole goal here is to cancel. I want to get rid of this 3. That's why I multiplied everything by 3. And I want to get rid of this x minus 2. That's why I multiplied everything by x minus 2. So what's left then is a 2 and an x plus 2. Over here, the same kind of thing happens. And over here, unfortunately, nothing cancels. Such is life. Right? So I don't know sometimes what this looks like to students, but to me, I'm like, this is way better, right? I don't like this one with the fractions. That makes me nervous. Here, at least I don't have any fractions, right? So let's just see what this turns into. X minus 2 times x plus 2, that one's a nice one to just multiply together because it gives me x squared minus 4. 2x plus 16 equals 9x squared minus 36. So now I want to think about what kind of equation do I have here, because that's going to tell me how I solve it. That's my big clue, right? I have an x squared, so this equation in class, I would have you all say it in unison, but here online, I'll just tell you. It's a quadratic, right? Because it's x squared. So I'd like to put this into standard form. I'm going to move everything over to keep the x squared positive. That's the standard form I like, is having the x squared positive. And then I subtract 16 from 36. I get minus 52. So when I look at this one, I'm thinking, okay, it's a quadratic, it's in standard form. I'm looking for 2 solutions. What about factoring? Right, I mean, I don't know, maybe it factors, but like to me, like this 9 and this 52, like I don't like those numbers. That looks like it's gonna be hard to factor, and maybe it won't even factor. Square root property, nope, it's not in the right form for that. Completing the square, nope, right? It's got all these complications. This 9 in front actually makes it harder for us to complete the square. So this is a quadratic formula. And it might be a little messy because that's 52, right? That's what I get for making up an example on the fly. But negative b plus or minus the square root of b squared minus 4 times a times c. All over 2 times a. Now I can see I'm going to have to get a calculator here probably, right? I probably wouldn't give you these big numbers. But be very careful. This is a negative 4 and a negative 52, so that's going to be a plus. 4 times 52 is 208. 208 times 9 is 1872. So that's 2 plus or minus the square root of 1876 over 18. I mean, I guess you'd probably simplify this. I don't think it's worth our time too much, right? We could maybe see if there's some perfect squares in there. But that's like, I would just start plugging in, like, is it divisible by 4? Is it divisible by 9? Just to see if there's any perfect squares in there. I don't know. if it is or not. So is that okay to leave that?
So that helps,
So,
helps a lot. Thank you.
Okay, yeah, that's an excellent question. Those are not, these are like, I think of these as sort of like, this is like a peak problem, right? Because it's like, it involves working with factoring. It involves working with fractions. It involves working with the quadratic formula. It's got like everything in our course all together. So if you can do a problem like this and sort of keep track of things as you're working through it, that's a really strong sign. You're in good shape moving forward. And even if you make a tiny arithmetic error in this problem, I would still feel good, right? A success.
Yeah,
if you get through there.
I was multiplying the denominator by the missing, like I think I would have multiplied 3x minus 2 times x plus 2 on accident.
Yeah. Well, it's not wrong. I mean, that's what's a little tricky about this, is that it's
messy.
Yeah, and there are steps that are wrong, right? Like if I multiply this side by x plus 2 and this side by 7, that's wrong, right? That's going to mess up the equation. But like, it sounded like what you're doing is not wrong, but it's not like it's getting messy and not necessarily leading us to the answer, right? So that's also tricky to just know how to attack it, right? Because as we move through math, you get more and more tools, right? You've got other ways you can change this around. And so it can be hard to sort of know which tools to apply. So again, I think a general rule, and I tell this to my calculus class, and is if you see an equation with fractions, just get rid of the fractions. It'll always give you an equation that's better than what you started with. And you'll be more likely to sort of know how to finish that equation.
Yeah, and I always wondered that why is it not -2, but it's -52?
For
when you plug it in.
For here?
Yeah.
Yeah, so remember the formula. The formula says it's -b.
Right.
So whatever b is, the negative b means you actually take the opposite. So in this case, the b here is -2. So the opposite of that is actually +2.
Okay.
Okay. The part here, this is a negative as well, -4ac, but I just keep the a and the c as they are.
Yeah, I didn't see that. Yeah.
Does that, and that's an important question, because that's a very easy spot to make a little error. That's like most of the errors I see with the quadratic formula are not going from here to here. You know, once you figure it out, most people put in the right numbers for A, B, and C, but it's getting tangled up with like what's a negative and how does that work together. So you want to make sure that you see that. And the safest way is just to like, I mean, it might even be safer, I don't know, to write that, right? That's really -b. But of course, negative and negative is a plus. So that's why we sort of put that in directly. Okay. Other questions about this problem, or? It's you know, if some of you are feeling a little, you know, whoa, blown away, it's you actually probably have the skills to do each of these steps. It's linking them all together that's challenging for students, and that's part of our kind of growth as mathematicians, is that we are able to see a problem as like a plan, like I'm trying to go from here to here. Simple problems, you just go directly, right? It's like I want to solve this simple little equation. I know what I'm going to do, and then I just do it, right? But when you have a big problem, like this, it's like, I don't quite know how that's all going to work out. I can't see the end of it. And that can feel kind of like, I can't do it, right? Because I don't know. But we have to trust ourselves and say, well, I'm going to start to change it and work through it. And then at some point, wherever that is along the way, maybe you get to here, and then you're like, okay, I know how to solve quadratics. I know how this is going to go, and then I kind of complete the work. But until you get to that point, that can be a different feeling for students. So that's something to get comfortable with, and don't shut down. I guess that's the number one thing. If you've done your homework and done your work and listen, you know a lot of what you need to do. So show that, right? Especially on the final exam, right? If you get stymied halfway through, it happens sometimes, right? But you can't just leave it blank and be like, I don't know, because that's not gonna cut it, right? You got to show like, okay, I know I gotta do something with the denominators, so let's just factor them and see if that kind of sparks something, right? And that's what a sort of problem solver does, right? And that's really what we're trying to teach you guys in math, right? Some of it is the algebra. I'm not confident how many of you are going to, solve equations like this at work. Some of you will, that you think you won't, but some of you will, but some of you won't, right? And that's okay, because it's really, there's also this underlying, like, how do I solve a problem, right? And whether it's in numbers or other things, that's still a skill that takes some learning. Okay, see, I get off track, but I'm back now. Are there any other math-related questions? Anything from the homework or? Oh, I see it. I missed the chat here. I missed these are old. Okay, S. All right, let's look at, yes, a couple questions I got from the homework. Okay, give me a second. It's slow coming up here. Okay. Just look through them and see if they're common. Yeah. Okay, yeah, so here's one. X minus 4 squared equals 81. The question, I don't like how they phrase the questions. 26. But they say extracting the square roots. I don't know, it's not really extracting. This is just the square root property is really all they're asking for here. So x minus 4 equals plus or minus the square root of 81. So x equals 4 plus or minus square root of 81 is 9. And of course I want to add those. So I get 4 plus 9, which is 13, and 4 minus 9, which is minus 5. So that, yeah, a lot of times students are confused on what they're trying to do there. That's all they're asking when they say extracting the square roots. I don't know, square root property. 11. Yeah, so 11 is a completing the square one, and we did one pretty similar to this. I'll get you started. So notice this one says on the assignment, solve by completing the square. On the final exam, I will give you one like this, and I will say solve by completing the square. All the others, I will just say solve, and I will let you choose which is the best method, which method you like. It's fine. So, So just so you're clear, do read the directions, because this one, if you just saw this one with no directions, I would expect you to use the quadratic formula. It turns out it doesn't factor. So that's normally what we would do, except I'm forced to use completing the square because I read the directions. So half of 4 is 2, and 2 squared is 4, so I'm going to add 4 to both sides. And that is going to make this a perfect square. And it turns out it's always half of this, x plus 2 squared. And you can check it, right, by foiling it out or just even factoring it to see that it's that. And then you can use the square root property just like that problem up above. And there was one other. Let me see. Oh yes, right, a quadratic equation that has the given solutions. So if the solutions should be 5 and negative 13, and I want a quadratic that has those solutions, and this is a little bit of a preview of like something you'll be thinking about in college algebra too, is that if I have a solution of 5, one way to generate those solutions is from a quadratic. And the easiest way is not through the quadratic formula probably, although, well, I don't know if you could do that or not. That sounds hard to me. It's just a puzzle maybe for another time. The easiest way is to do it through this factored form. So if 5 is a solution, x minus 5 has to be one of the factors, right? Because then when you solve that, x minus 5 equals 0, x equals 5. And the same way, if minus 13 is a solution, then x plus 13 has to be a factor. And then from that, I mean, you need it equal to 0, because otherwise those wouldn't be answers. From there, you can FOIL that together to get your quadratic. It says there's many correct answers. Well, it's sort of true. You could multiply in front by 17. That's still a quadratic, and it still has the same answers. I wouldn't expect anyone to do that, but you could. Okay. Okay. Anything else?
I have a question on number 6 from the Moore equations homework.
Yes, let's take a look at that. That's probably, we have not really talked about that very much. Yes, that's a good one. Let's take a look at that. Solve the equation, check your solutions. Normally, you can get away without checking your solutions, but when you're doing with square root equations, you actually do have to check your solutions because you can get ones that don't actually work, even if you do everything right. So there's 2 approaches to solve this one. One is just to treat it as a square root equation. I don't know if we've done a little bit of work with square roots. I'm not sure if we've done work with the squared equations. What you do is you would isolate the square root part. And then you would square both sides. When you square the square root, you'd get x. Now this over here would be a little bit of a nightmare, right? You have to square 19, which is a big number, and then you'd have to FOIL this out. You'd get a quadratic in the end, and you could eventually solve that. So that's one approach, but it's not really the approach that they're hoping for here. because it's in this kind of quadratic equation. So here's what we're going to do. We're going to set it equal to 0. And what I'd like you to recognize is that x is actually the same as the square root of x squared. And you might say, well, it doesn't make it look any better, right? I was happier with just the x. Well, notice what we have here is something that looks very similar to a quadratic. So this is called the quadratic in form, is kind of what I would refer to it as. It's not technically a quadratic because it's not actually like an x squared, but it has the same pattern as a quadratic. So it turns out you can factor it the same way you would a quadratic. So it's just instead of x, it's the square root of x, right? So this is like the 5x squared and the 19x and the minus 4, but it's square root of x for each of those. So you can factor it just like you would a quadratic. In order to get 19 in the middle, I need to have a plus 4 here, because that's going to give me 20 square roots of x, and a minus 1 there, which is going to give me 19 square roots of x, right? And those are going to give me minus 4, and that's going to give me that 5x, or 5 square roots of x squared. And factoring is great because now I can set each of these equal to 0. And I can solve them.
So you leave out the 19.
So the 19 comes from like when we FOIL these together. So I'm really doing this like I'm factoring, let's not call it x, 5y squared plus 19y minus 4. So I want to get that 19, but that 19 is going to come from FOILing these two together. Put a plus 4 there, minus 1. So this product, 4 times 5y, gives me 20y. And that gives me minus 1y. And that's what generates that 19y.
Okay.
And whether you call it y or you just keep it as the square root of x, I kind of like to just keep it as the square root of x, because if you make it into y, then you have to remember it's not really y, it's actually the square root of x. This particular version is a little hard. The factoring here to me is a little bit hard. I would prefer one that was easier to factor so that you could see it more clearly. Square root of x equals minus 2. Now be careful here, I'm not using the square root property, I'm actually going to square both sides. So there's no plus or minus. And this one, the square root of x equals minus 2, that's not possible. Square roots are always positive numbers. So there's no I that works there. It's not that situation. It's square root is not equal to -2. So it turns out the only answer there is 1/25. So there's sort of, again, like 2 parts to the problem. The first part, which is in some ways maybe the most critical part, is recognizing that this is a quadratic that we can attack with our kind of similar methods. And then the second part, which is maybe more work, is like actually solving these sort of little equations that we get. Does that help? Does that seem?
Yeah, that helps.
It's about kind of seeing the whole process, you know, like, okay, what am I trying to do? And in a lot of ways, that's what matters the most to me, is that you guys see that process. sometimes the details get a little messy, right? Or the factoring gets off, and that does make a difference. But if you can show me that you sort of understand the process, then I feel really confident that maybe you didn't quite get it this time, but you would the next time. So the process here is that we're trying to factor this to break it down. Because if I can break it down into these two parts, then I can solve it. When it's all together, I sort of can't. It's too much. Okay. Yeah, oh, you're very welcome. Anything else? You've all had very good questions. I think they've benefited your whole class, right? Those are good questions because everyone has things they can learn from those. Yeah, so there's a question about the final. Yeah, it should be a similar length to the midterm. There's a little information about it in the schedule, and I will, I'll post, kind of like I did before, I will post a review list of topics. It will focus on the new topics that we've covered mostly, but there's a little bit of our previous topics too, and I'll list those in my section. So I don't want you to have forgotten totally about graphing lines or, well, obviously you have to work with factoring and polynomials. Those are necessary to working with quadratics. But, and you'll see in our next section, we're doing some more work a little bit with lines. And so it does connect to our first half of the course as well. But I forget what I said, but it's roughly about 75% will be the sort of new material since the midterm. Yeah, anything else? Okay. I will let you guys go.